In this video, we are going to learn about yet another form of complex numbers, the exponential form, and we also get to know this very important and useful result, Euler's formula. So what I would like to start with is to tell you about Euler's number. Euler's number, it's a mathematical constant that pops up in many places. It's denoted by E, and it has the decimal expansion of 2.718 and so on. It's an irrational number that is often defined as the sum, and I will use quotation marks around this word sum because it's going to be an infinite sum, and that is something we are not used to yet. So E can be defined as the sum 1 plus the sum of the reciprocals of factorials. So 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on. You get the idea. So this is how this number can be defined. We'll understand what it really means to add infinitely many terms later on in the module. Now we just I just want you to see this way of expressing E or defining E, and in fact more generally we have the following. We have the exponential of any real number x can be written as 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. So you see where this is going. We have powers of x divided by the corresponding factorial, and we add all these up. This way we get what's called a power series, a series expansion for this function, the exponential. We are not going to establish the validity of this result. This is for your calculus module. What I would like you to just notice that we have this expansion for e to the x, and similarly, well, let me just call this fact number 1. It's not just the exponential function for which we have such an expansion, but also the trigonometric functions, our good old friends, the sine and cosine functions. Also have such expansions. Namely, for the sine of x, we have the following. We have x minus x cubed divided by 3 factorial plus x to the 5th power divided by 5 factorial minus x to the 7th divided by 7 factorial plus and so on. So what's happening is we are taking odd powers of x with alternating sign. So the signs change, they take turns plus and minus, and we divide these powers of x by the factorials of odd numbers. So this is the series expansion for the sine of x. Similarly, for the cosine of x, we can write 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the power 6 over 6 factorial plus and minus and so on. So you get the idea. Fact number 2 is that these 3 series for the exponential, the sine and cosine functions also make sense for complex numbers. The 3 series also make sense, can be made sense for x being replaced by a complex number. And in fact, for any complex numbers z1 and z2, it is true that we still have this nice property of the exponential function that is the following. If we take the exponential of z1 plus z2, that's the same thing as taking the exponential of z1 and multiplying it by the exponential of z2. So this is true for all complex numbers z1 and z2. Okay, so this is fact number 2, and well, we can use these facts, these results, to look at the following. So what I would like you to do is to take the series for e to the x, and we'll set x to be I times phi, with phi being some real number. Then we have the following. So just plug in I times phi for x, and what you will see is e to the I phi is the following. Let's start by expanding these, by going through this expansion. We have 1 plus I times phi divided by 1 factorial plus I phi squared divided by 2 factorial, and so on. So we have powers of I times phi divided by the factorials. And what I would like you to notice, let me just write out the 4th power as well, is that using the relation, so using the relation that I squared is equal to -1, this is the main defining relation of complex numbers, we can rewrite this expansion. Well, you will see the powers of I appearing, and for example in this 3rd term we have I squared giving us -1 times phi squared over 2 factorial. So that's actually a real number, real term, because phi was a real number. And similarly, the 2 terms down the line, this 4th power of I is going to give us, well, you have to square this relation to get I to the 4, that's +1, leaving you +1, so that's phi to the 4 divided by 4 factorial. So let's collect the 1st, 3rd, 5th, and so on, the even number terms. To get the following, we get 1 minus phi squared over 2 factorial, then, as I said, +1 times phi to the 4th over 4 factorial, and you can probably convince yourself that the next one is phi to the 6th power over 6 factorial with a minus sign, then a plus sign, and so on. This is going to keep going for the odd number terms. For the even number terms, we'll have I appearing in all of them. So in the first one, we have, of course, phi just by itself. Then here we are going to have I cubed, which is I times I squared. So I times -1. So that's a -1 times I times phi cubed divided by 3 factorial. Then for the 5th power, for the term with the 5th power, we will have plus phi to the 5th power divided by 5 factorial, then minus, and so on. You can probably see the rest of the terms for yourself. Just convince yourself that this pattern is going to continue. What I want you to notice now, that the real part of this series, this expansion, is nothing but the cosine of phi. So if you look at the series for the cosine of x and replace x by phi, you will get the cosine of phi here, okay, as the real part. For the terms multiplying the imaginary unit I, you will see similarly the series expansion of the sine of phi appearing. So this is the sine of phi that multiplies I. So in summary, we have this beautiful result connecting the exponential function via taking the exponential of I times phi with the trigonometric functions, expressing e to the I phi as the cosine of phi plus I times the sine of phi. So this is a very important and useful formula. It's called Euler's formula. Okay. What I would like you to do now is to imagine, well, we had this game raising I to various powers. I would like you to check your understanding by pausing the video and giving me the answer to this expression. Could you express it in terms of I, the 100th power of I? Pause the video and input the answer in the box below. Okay, so I hope you pause the video and basically realize that I to the 100th power is the same thing as I to the 4th power to the 25th power. The reason I would write it like this, because this is I squared, which is just plus 1. So this is just plus 1 to the 25th power. That's just plus 1. Okay, so I hope you got it right. Let's continue. So using Euler's formula, we can now realize something very important. We can realize that what we have on the right-hand side of in Euler's formula is basically what we had in the polar form of complex numbers. So previously, when we have written that z, a complex number, is equal to x plus yi, and then we turned that into a polar form of r times the cosine of phi plus I times the sine of phi, with r being the modulus of our number and phi being the argument of that number. Now what we have is what multiplies r can be written as e to the I times phi. So now our complex number can also be written in a third way, and this is the exponential form of our complex number. This is r times e to the I phi. Okay, so this is the exponential form. Of z. Now we have three ways of writing a complex number: the algebraic form, the polar form, and the exponential form. And to finish the video, I would like you to consider the following number. So to have this example, e to the I pi over 2. So I would like you to calculate this number and give me this number in its algebraic form. So pause the video, calculate the number, and input it in its algebraic form. Okay, I hope you pause the video. So if you apply Euler's formula, you will get for this number, which has I times pi over 2 in the exponent, the cosine of pi over 2. Remember, pi over 2 radians is just 90 degrees. So plus the sine of pi over 2. Now you have to remember that what's the cosine and sine of 90 degrees? Well, the cosine of 90 degrees pi over 2 radians is 0. And the sine of pi over 2 is equal to 1. So this is just 1 times I. So what we really get here is the imaginary unit being expressed in its exponential form. Okay? So, well, there is only one thing that is left at this point, which is picking a very special value for phi. This is just to finish the video. So some people claim that this next formula is the most beautiful formula in all of mathematics, and you get it when you replace phi by pi radians. You get I e to the pi I plus 1 equals 0. This is Euler's identity, and according to many people, this is the most beautiful formula in mathematics. You get it by replacing phi by pi there and rearranging that equality. Okay, I'll see you in the next one.